Section 6.4, Exponential Growth and Decay. So the first part of this section talks about the law of exponential change, which states that if the rate of change of a variable is proportional to the value of y, an equation can be written as follows. dy dt is equal to ky, where k is a proportional constant, which tells you how y is increasing in terms of t. So to solve for y, we have to separate the variables so that we can identify what the actual equation for this differential equation is. So we're going to solve for y using the method of separation of variables. So we have dy dt equals ky. So we're going to multiply both sides by dt. And then we're also going to divide both sides by y. So what we get in that sense, we get 1 over y is equal to, 1 over y dy is equal to ky, k dt. My apologies. Alright, so from here we're going to integrate to get rid of the dy and the dt. The antiderivative of 1 over y is ln y. Absolute value of y. And the antiderivative of k in terms of t is kt plus c. So to solve this for y, we're going to raise all of this so that it is the exponent on e, so that we can cancel out the ln and the e. So we're left with absolute value of y is equal to e to the kt plus c. And using law of exponents, we can rewrite e to the kt plus c as e to the kt, e to the c. And over here we still have the absolute value of y. So now we can get rid of the absolute value sign, but in order to do that, we have to make sure that we're taking into account that the right side of my equation can then be either positive or negative. So when I take away the absolute value sign, that is equal to positive or negative. I'm just going to rearrange the e to the kt, e to the c, so that e to the c is up front, e to the kt. So the reason why I rearranged e to the c and e to the kt is because e is a number that we are raising, that we are now going to give an exponent, which is also a number, right? So e to a constant is still just a constant. It's still just a value. And whether that value is positive or negative doesn't change the fact that it's still just a value. So e, positive, negative, e to the c can be rewritten as just c. If you want to make it a bigger c, you can do so, but it's just c. And then we still have e to the kt. So dy dt equaling ky. Once you've solved that differential equation, you get the equation y equals c e to the kt. So if you have a y that changes at a rate proportional to the amount present, then your equation, your general solution, is y equals c e to the kt, where c is the initial value of y, k is the proportional constant, and you'll get growth when k is greater than 0, and you'll get decay when k is less than 0. We're going to do a few examples. Okay, so our first example, we want to suppose an experimental population of fruit flies increased according to the law of exponential growth. So this is telling us that we have exponential growth. there were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximately how many flies were in the original population? So, because we know that this is a law of exponential growth problem, we know that our general solution is going to be in the form y equals c e to the kt. So in order to solve this problem, we're going to need to know c and k so that we can plug in a t of 0, right? The original population occurs at t equals 0. So before we can do anything with this equation, we're going to create a table so that we can see what information we actually have from this problem. So our table is going to be split into t and y, where t in this case is days and y is number of flies. So the information that we have is that on the second day we have 100 flies. So on day 2 we have 100 flies. On the fourth day we have 300 flies. So day 4 we have 300, and we're looking for the initial population. So we're looking for when t is 0, how many flies will we have? So we're going to use these two pieces of information to help us figure out c and k. So starting with this first row, we know that we have 100 flies when the time was 2 days. So 100 is equal to c e to the 2k. So if we solve for c, we'll get 100 over e to the 2k is equal to c. We also know that 300 flies were present 4 days later. So to solve for c here, we have 300 over e to the 4k is equal to c. So because both of these are equal to c, we can set them equal to each other. So 100 e to the 2k is equal to 300 over e to the 4k. We can cross multiply and divide here, so we get 100 e to the 4k is equal to 300 e to the 2k. And then if we divide this side by 100, e to the 2k and 100 e to the 2k, we'll get that 3 is equal to e to the 2k. So then, to get k by itself, we'll take the ln of both sides. Ln will cancel out with e. So 2k is equal to ln of 3 divided by 2. K equals ln of 3 over 2. So now, using that information, we're going to plug in our k to find our c. So we know that c is equal to 100 over e to the 2k. So we're going to use that and plug in our k. So c is equal to 100 over e to the 2 times ln 3 over 2. The 2's will cancel, and we'll get c is equal to 100 over e to the ln of 3. E to the ln of 3 cancels out, and we get that c is equal to 100 over 3. So our particular solution here, kind of all over the place, our particular solution is that y equals 100 over 3 e to the ln of 3 over 2 t. And we want to know when t equals 0. So we'll plug in 0 for t, and we'll get y equals 100 over 3 e to the 0. So y equals 100 over 3, which is approximately 33 flies. Alright, for question 2, we're told that 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. If the sales follow an exponential pattern of decline, so again we still have an exponential pattern, what will they be after another 2 months? So because we know we're following an exponential pattern, we know that y is going to equal c e to the kt. So we're going to create our table where t is in terms of months and y is in terms of units per month. So the information that it gives us is that sales have dropped from 100,000 units to 80,000 units 4 months after it stopped advertising. So 4 months later, we're at 80,000 units per month, which means we started with 100,000 units per month. So then, if we're looking for another 2 months, so 2 months after 4 months, we're looking for 6 months, and that's our question mark. Right, 6 months, how many units per month? So in this case, remembering that C is going to be our initial condition, right? Our initial condition is 100,000 units per month. So our C happens at our initial condition, so at 100, so our C is going to be 100,000 units per month. So then, if we wanted to double check that, we could plug in 100,000 equals C e to the k times 0. So 100,000 is equal to C times 1, which is just C. So then we have y equals 100,000 e to the k t. So using our second piece of information, we can plug in 80,000 equals 100,000 e to the 4k, because it's 4 months. And then we're solving for k. So if we divide by 100,000, we get 0.8 is equal to e to the 4k. We'll take the ln of both sides to cancel out the e. So ln of 0.8 is equal to 4k. And then divide by 4. So k is equal to ln of 0.8 over 4, which is approximately negative 0.05579. So I found the decimal version of this so that when we plug it into our equation to find our y, we can just use a calculator to plug in a numeric value for k instead of trying to plug in ln of 0.8 over 4 into our calculator and making a small error. So our particular solution is going to be y equals 100,000 e to the kt, and we want t to equal 6. So we have y equals 100,000 e to the 6th k, and we know k is negative 0.05579. So when we plug that in for k and type it into our calculators, we'll get that y is approximately 71,554.175 units per month. I'll make a separate video for the Newton's Law of Cooling examples, the last two examples for 6.4, so look out for those two examples in the last video.